to go live and then we can start the session. Perfect. Okay, I think we have started. Yeah, so thank you so much everyone for joining in. Like I said, I'm Nancy and the program's lead for She Hacks. Thank you for making time to join us tonight. So for tonight, we have an in-depth session. I believe we have a guru here with us to take us through today's session. So without further ado, I'll invite you, the speaker. I can see the speaker is already on call. So let me just make you co-host. Yeah, so karibu sana Chu. I think you'll introduce yourself so that I don't butcher your titles. Yeah, you can tell us about yourself. Then maybe if you need to share your screen as well, you can just test that. I hope that's okay. So, yeah.
All right. I don't know. You can hear me, right? I'm audible. I hope so. All right. Thank you for having me here. I don't know if you can hear me properly or I'm a little bit down. Let me put on my mic up. Yep. I'm audible. Hello. Hello.
Yes, we can hear you.
All right. Okay.
We can hear you.
Let me just kill my messages like Teams and Signals so no one calls me during the session. The time I was doing some presentation and then my family was calling me overseas and I was like, now what I'm going to do now? And it all went live together with the recording. Anyway, I don't want that to happen anymore. So I just learned that I need to make sure that all my messages are off before I go live. Thank you for having me. My name is Chucks. People call me Chucks. It's from the name Geshuki. A lot of people are not able to call me Chucks whenever I'm working with the guys overseas most of the time. So they just call me Chucks and it is stuck. I didn't get time to prepare a presentation at PPTX. There were no lights since yesterday. Welcome to Nairobi. So the only thing I can do now is mostly just walk you through on some of the stuff you might have to require to understand how to look into Linux implants. So what I'm going to do is that before we go through all that, I'm going to share my screen and I'm going to give you one of the servers you can use, which is already infected with BPFDoor. It's a live server. I just bought it a few minutes ago so that you can use it for this training. You can play with it until next week before I shut it down. I'm going to share my screen so I can show you that machine. It's been a while since I used Zoom. I hope it can actually be able to do the right thing. Yep. All right, the server is on 23254.226.117, and this is the password you can use, and the username is router. So let me just do that. 23254.226.117. All right, for those who are in the lobby, this is the lobby. This is where every magic is, all the magic is happening. And this is a machine that was infected. So if you go to if you use Guacamole via the web, it takes you directly to where the server is. We had to put 3 samples, which are the same actually. The only thing is a little bit of size, but this is what we call a dynamic link. This is a normal ELF. It's a normal ELF. I'm going to discuss about all those things later on, so that we can all be in the same level of understanding. All right. So before we go further, I usually like to do some notes. I'll just try to make them up as big as possible. And they're going to be on subheadings, I think. I usually let people know one thing. Since now we are in the information age, things are really different from what we used to do back in the days. When you're doing analysis of malware or even any form of DFIR. I think I need to admit that guy, whoever it is. All right, so I don't know if that's the best font. Okay, you can see my fonts, right? Everyone?
Yes, we can.
Yes.
All right, let's continue with that then. So one thing you gotta know is that those developers who write implants, or those developers who write toolkits that are used for maybe computer network operations, or maybe even normal operations to do financial attacks, they usually write those tools knowing that they might be caught. So what they have done is that they have implemented things we call defensive evasion. So you find that need to keep changing the fonts then. So you find that as they write these tools, back in the days, you could write a tool in C, C++, and it could be what we call a Linux malware, right? So a Linux malware by default will have a header which goes to a header which starts with ELF. So, but a C++ malware written for Windows will always start with a header which is called the MZ. So back in the days, whenever we had this type of malware coming in, we always analyzed it on Linux machines too. All of them. This is the old school because there was no defensive evasion then. This is old school analysis. Because by then, guys were not looking into how they need to fix their toolkits. They need to fix their toolkits so that they cannot be caught during the operations. There was nothing like that back in the days. So these days, modern ops during analysis. My fonts are not so good. It's because of this. Okay, let me just move it. Tighter. So because of the modern ops, how the operators actually making their toolkits, you find that malware written for Windows has to be analyzed on a Windows machine. So what you do is that you create machines that you can use and dump and create again and use and dump, because you might be looking at a lot of things on memory level so that you can actually dump that memory and actually analyze it. Or you might be doing a lot of debugging to actually get the payload you're looking for when analyzing a malware written for Windows. The same thing happens in Linux. Same thing happens with Linux. You find in Linux that in modern levels, some actors are actually making sure that their toolkits are having defensive capabilities. Now, the good thing is that this backdoor that was used by the team from China that were using this capability to actually be in a position to run operations across the world, did not develop this tool, which was actually written in C++ for Linux, using the normal Unix API. I think you guys know of it because it's almost like the way we write it with the way we write Windows API toolkits. It's almost the same way, only that we have a different way of calling the headers and also a different way of actually calling the parameters and functions, and also typecasting is very different in Unix API toolkitting. So I'll make sure that it's big enough for us to see. So as you can see, as you are going to see when you start analyzing the backdoors that are used by this team, you'll see that it's actually simple. It's actually very simple to actually look into it, and also it's also very simple to write one. You don't have to do a lot of defensive capabilities on Linux unless you know the infrastructure you're going for has some of the best people who actually look into how tools and how attackers are actually going after them. There are those organizations which have what you call a very huge threat matrix, like let's say a mobile network operator. That organization should have some of the best people on SOC, people who have been doing a lot of cyber warfare capabilities, or they have been actually having a good background in cyber warfare, because you find that such companies are targets for organizations who are on APT level, like let's say US Cyber Command, China PLA, or China MSS. All those organizations will want to know what Safaricom, or rather Safaricom, or maybe Airtel, or all those things, what they have in the databases. So you find such companies should have some of the best people who know how to analyze, on how to catch high capability APTs. And that requires that if that happens, then the APT has to be in a position to write code which won't be analyzed in a faster way. So APTs versus fin groups. All right, so APTs by default, they work for military organizations. They work for sorry. They work for intelligence organizations, and also they will be part of what we call defensive contracting. Defensive contracting or defense contracting contractors. I think I need to know how I need to move this thing, because it keeps coming on top. Or do I just cancel? Someone else can work on it. All right, so APTs, they're usually mostly military organizations. And they can also be intelligence organizations or defensive contractors, who by default will try to to support the countries or the hosting country that they are in on operations. Then we have fin groups. These are actually just organized crime. This thing I need to stop. I don't know. I think it's because I'm one of the hosts members. That's why I'm getting this. I don't know. All right, fin groups are organized criminals. All right, organized crime. Mostly they are just after the money. So for them is more about how fast they can get in and get the loot that they need for the objective. So most of them, they can actually, they don't mind being noisy in a network. So these are easy to catch. So that's why you see a lot of them sending like a million a million spam emails, a million documents, which are malicious documents and all that. But these guys are going to be slow and stealth as much as they can, because their objective is about being there for as many years, as possible. Now, let's talk about China. China has it has the biggest APT network ever seen in the world. These guys, the funny thing is that they started before even the US, because by 2000, they were already breaking into different organizations. But that time they were not so professional. Until they realized the US NSA was running some better operations for cyber ops. So what they did is that they had to structure how they run operations, and a lot of groups were actually used as cutouts. Others were used as the main contractors, and others groups were used as researchers and operators, just running operations from the universities and campuses, and others directly worked for the PLA. All right. So the analysis of this toolkit we're going to look at, it's called the B, which is such, it stands I think for Berkeley sampling protocol, and also packet filter. It actually goes through filtering the packets in a way that the firewall will allow it, because it's just there at the front of the firewall as the packets come. It can go through any service port to connect to the target machine that they actually want to target from a remote machine that they have somewhere that knows the magic packet, for it to connect to that implant for the operator on the other side to be in a position to control the machine they have infected. So it's called a Berkeley Packet Filter Door. This toolkit, there is high likelihood it was developed by APT41, but also it was used by APT31, if I'm not wrong, which is also called something mention. I'm forgetting. Mention, yeah. Can you guys remind me the full name of this operator using that keyword that they use? I think it is PWC, which came up with it. There are so many names right now for APTs, but I like tracking them with the FireEye naming convention more, because FireEye naming convention uses more of APT numbers. And I think it's a better way to actually be in a position to actually classify APTs as they come up. So the amazing thing about APT41 is that they are based on a place called the Chengdu or something like that. I'm forgetting. I've not done much research lately on APT41, but last year if you asked me, I would have told you everything about them. But I know I'll be coming back to it in a while, because I'm supposed to do some work on APT41 very soon. APT41 has the best coders in China. It looks like they are the ones who do most of the tooling, because you find any APT that is from China, APT41 will have their toolkit in your arsenal in some way or another during the operations, which means APT41 might have the whole source code or the whole repo for BPFDoor in a way. So we might, and you know that APT41 targets every country, including Africa, and there's high possibility they have run operations in Africa in several ways. We have got a lot of China activities in Kenyan government, but that's the story of another day. All right, any questions so far before we now go to the analysis of everything? All right, we go on. Okay, so so far as BPFDoor is concerned, the user or the operator who is running operations on target does not do any, there is no persistency after exploiting the target. And also, so this requires that the operator, the CNO operator from China, has to put their own level, their own version of persisting on target. The other thing is make sure that for the binary to run on target system, the operator, the CNO operator, has to have sudo access, which means these guys will need to have already compromised the machine. The target system to actually be in a position to actually push the binary. Maybe they pushed by maybe downloading or via SFTP on the target system to make sure they can control it from remote. And then they do the persistency to make sure that whenever it comes up, the machine reboots or anything, depending on what they are actually looking for, they allow that to happen. All right, let's go look at some of these tools that that were used by these targets. So I'm hoping that all the things I'm going to do are going to help us make sure that you can actually be able to be in a position to answer the questions that are coming up. So one thing you can note is that China, or the operators who are running these operations, they made sure that the tools they're using for operations are using the naming convention of processes in Unix and Linux system, or Solaris, or whatever system they're going for, to actually be in a position to hide themselves. So like now, if we do a ps out grep AGT, you'll notice we have a real process called AGT, whatever that is. And if you do what is AGT2Y, okay, sorry, really badly. Not showing on this one. I don't know why, but on a default Linux, it will tell you what AGT does. You see, it's a tool which comes up with Linux. It's a normal tool which is used by by Linux systems. Also, CAPS 3 is another one that you actually find a lot on Linux and Unix systems. So, which tells us that these guys were cautious when it comes to running the implant on a target system. So I know a lot of people asking what an implant is. Let me just explain it here. Implant. All right, so an implant, by default, will be a toolkit that has large capabilities to either download on target system, just like the way CobaStrike does, but CobaStrike is a framework which has a lot of things all embedded together. So download these things which are popping up, download, edit, surveil, upload data. And a new thing that we are doing these days during operations is cloning the network, cloning the systems, clone, intercept. What's the thing that we do with implants whenever you have them on a target system? Evade, analyze for exfil, or for expectation of data. So it has that capability. It has some level of kind of an AI in a way to actually be in a position to know what is supposed to exfil of the target system. What else? There are several ways. There's several things that an implant will do. But usually, by default, an implant will be brought in after several other stages by the actor. So the actors will need to do a lot of staging to bring the last thing here. And then also we have another version of an implant. Another version of implant usually used during operations, which is actually after the end of everything. The last implant, let's call it last stage. We call this implant a housekeeping implant. So by default, when you look at this implant, if you look at this implant that's being used by this team, the BPFDoor, you'll notice BPFDoor is actually a housekeeping implant, in a way that they had already finished whatever they were doing, and then they left this backdoor later on, or this implant later on, for much later access, if you want to go back to that infrastructure for much more exploitation. So by default, what happens is that the housekeeping implant will help the operators to clean all the other tools in the environment, make sure they're not detected, and then push this implant on a machine that they know people will never look at. The machine is always on. The machine is always, maybe it's old, it's somewhere on a corner. So they will drop that implant there. And then maybe 5 years later, when the director or the general comes and tells them, we want to look at what Safaricom is doing for the last 5 years. Can you go and get everything that is there? So what they do is they just call the backdoor, and then backdoor will just open their way in, and then they will laterally move to their machines, pushing their new implants on target for collection. All right, so let's go and now do the analysis of the files. I hope that background was enough for us to look at. I'm going to make sure that we don't go so deep on this tool. We're just going to make sure that all the questions were asked on during the analysis of this toolkit are in a position, in a way you can actually be in a position to answer them. All right, so the first thing you'll do obviously is to make sure you know what type of file this is. So by therefore, if you look at it, it will tell you obviously it's a 2-bit ELF file. And you remember here when you talked about all this stuff, we said a Linux file, a Linux binary will always be called an ELF file. If it was a Windows file, we could have seen it as a different level of headers when you look at them using the command file. So if you want to see the first line of the header of this binary, you can use a toolkit called, I don't know if it's installed here, HXD. By default, it should be there. HXD, let me see. If it's not there, we can always do HD. It's not there, so HD. Yes, it's there. So what you're going to do is just make sure we see it in, we look at it in steps or in pages. And you can see the first thing that actually opens up is ELF, which actually is 7F45 or that way. That's the header that comes up when you look at an ELF file, which tells us this is a real Linux binary, which means for us to analyze this file, we need to use a toolkit that is going to open a Linux file inside Linux. Like now you can see you're actually using a Linux machine, and you can actually be able to analyze this binary using the toolkit that you're going to have on our desktop. So the best way to actually analyze this is by going via either Pro or either freeware, and it will actually be in a position to help you to analyze this file. So let's open up either. And we are going to go to desktop and dataset. And malware analysis and challenge. And you're going to open a Getty. And obviously to tell you what type of file it is. So go ahead and accept, because it's a 386 ELF file. Yes, sir. Let's go in and okay, that's okay. Okay, that's okay. We can still work with it. And it will open up the binary on either. All right. 1 minute to 2 minutes break for any question so that I don't lose anyone. Any question?
Okay, if you have a question, maybe you can have it in the chat. I will be sure to read it to our guest, or maybe you can try and unmute if you feel you like it better that way.
All right, let me look at them before we continue so that I make sure that we don't lose anyone. You're audible. No one asked anything, so you're good.
Yeah.
I'm sure told sometimes I might go too fast, so I try not to do that as much as I can. All right. So one thing, as we said, when you looked at this binary, we realized it's a Linux binary. So by default, back the days, because people still don't do much of encryption or doing any defensive evasion when writing their malware for Linux. Actually, if you do strings on this implant, you will notice that they have not encrypted anything. So let's just look at it to see. You can see actually. Yep. Someone says something. Someone is trying to talk. All right. So you notice that it's actually doing some stuff with sockets, H1 shots, how it's doing the connection, the string and copy, all these APIs that also you can see on Windows sometimes. It's also doing some level of mem setting, all that stuff. And the amazing thing is that this toolkit is not there's no level of encryption or any level of security I've used, except maybe the authentication of the command and control or the controller on the other side of targeting, which is actually a very funny thing, because this is how we used to see malware back in the days for Linux. This is how we just needed 2 strings, and we are finished analyzing that we already understood what it's doing. But anyway, the good thing is that we have IDA, which can actually give us a map of what the implant does. So let's just look at it. So by default, the first thing you do whenever you upload an implant on IDA is to go at exports and to look at the exports that it's actually pushing in. So one of them, you can see it's actually environment. The other one is start, and this is where it starts doing the executions, which is the main entry. So by default, this being the main entry, it should be the int main of this implant when it's opened by the target, or when actually they were doing the coding. So if you double click on this, it actually takes you to the map of the entry, and it can show you exactly from which part of the memory it goes from the part of the communication. I don't know why my internet is a little bit slow. I can't push. Okay, there it is, and all that stuff. The other export you can view is this environment, which actually is like one of the exports they actually took in. Let's just look at it. Okay, goes to your business. Okay, all right. Let's look at this other input output SDI used. These are some of the other exports these guys looked at. I don't know why my internet is kind of misbehaving today. I think it's because I had power issues the whole day, and I'm clicking and then it takes whatever to bring it back. Okay, let's just leave exports there. All right, let's look at the imports. The other part of the analysis you look at is mostly the imports. Jesus Christ, my internet. Is it cyber rages or my internet? Okay, let's just close here and go back in. Let's hope it works this time. I'll just close it and try to view it again. Okay, then I think I should be able to get it back where it was. Welcome to the internet issues. All right, I think I'll just work with it where it is. All right, so the imports are usually, this is where you have the address of the import. This is the ordinal number. So by default, if it's actually on Windows, you can actually see the number of the ordinal. But in Linux, we don't mostly look at that a lot. On here, we have the name of the import. So the import is actually a Linux API or Unix API. And you can actually be able to tell all those imports we saw when you're looking at the strings of the toolkit. Some of them are things like htone, read, vhangup, all that stuff. They're all here. The sockets, all that connection, they're all here. Also, you can see, look at things like bind, the string copy, the unlock, all that stuff. They're all there, or they receive from, all that stuff. They're there. So what we want to do is that we want to follow how the execution works on this implant. But now the problem I'm having is internet issues, or rather maybe the cyber edges issues. I don't know. I don't know. Anyway, you work with what you have. So the EDA view, just go to the EDA view of the toolkit, and what you want to do is go back and go to the main where it starts. And you can tell one thing is that that's the normal ZOR way to actually make sure that we start on a clean slate. Is there any question? I hate it when the internet misbehaves, so I'll just go back again to input. All right. So first things first. It's actually good to look at the APIs directly. Okay, that's the next intern. Listen. Yes, I can't find it. Okay, I'll just do the hardcore way. I didn't want to take you down that structure. All right. I'll just start with the hardcore part of the level. All right. Just give me a minute. I get it. I get what it is. I get what it starts from. It looks like I can still find it. All right, here we are. Okay, it looks like we need to start directly for the main start, but we have to look at the export directly because from here we can't do the things we need to look at. And what I'm going to do is that I'm going to just make sure that we can see this table properly. So for you to actually look at it, you can do control and then the mouse. You just call the mouse and it will take you to the entry point of where the offset starts for this toolkit. So one thing you can tell, what you want to do is we want to go to where it starts the data call, which goes to this memory point, and I don't know why it's not taking us the right place for the socket. It's not giving us what you're looking for. Okay. All right. Looks like you have to go the simpler way, the other way around, where the strings. Okay, here we are. This is a better view. All right. So one thing you have to tell, one thing you have to know is that one thing is that we are looking at is actually derouting and working through using the IP tables in a way that it actually directs the ports so that it can actually hook in and be in a position to connect to the go through the firewall on the other side and be in a position to direct its ports and be able to transfer that packet over to the machine that's actually infecting. The other thing you can see is that it kind of tries to, let's look at it. Yeah. Here is the list of the files to try to mimic. So it might mimic itself as Migeti. It might mimic itself as a normal debug session. It actually loops through, figure out the name that's going to use. And then the next thing it does, it will go ahead and try to, to open a file name, or rather a PID name, and then it will lock into it. And the PID name it's using here is CXINETD, which is actually going to be on val run zin on the log file. So let's just start now doing the report as we analyze this. So I'm going to go back to where we started from so that we don't get lost, because I've just figured out where the problem was. So yeah, there. So I'm going to actually open up here, and we are going to have our notes from here. Notes for the analysis. All right. So we are going to use strings this time because it's not encrypted anyway. If it was encrypted, we would be having a bigger issue to understand where we start from. We are going to start, first of all, look at hit this connection. See the way it is jumping. Yeah, this is an internet problem, internet connection problem. I should have done this on my local machine, the analysis training. Okay, we are back. So we are going to look at this. You're going to start this way. You're going to start the part of analysis from drill out, and amazing. I should have done the analysis from my local machine. Internet is really failing me right now. Come on. Can I switch to another network as you push your questions? I log off and switch to another network. Moderator?
Yeah, sure. Yeah, that's okay. That's okay.
Okay. All right.
Yeah.
Let me switch to a different network because this one is becoming a problem for me. I'll be right back in 2 minutes or less.
Okay, sure. So has everyone been able to access the lobby? I shared the link. Let me just share our chat. Next. Yeah, so I have shared the link in case maybe you want to join. Lawrence, for how long will this lobby be available? Or it ends when the session ends? I don't know if you're able to unmute.
Hi, Nancy.
Hi.
So I think the lobby will still be on for a couple more hours, maybe 2 or 3 more hours after you join. So the moment you join the lobby, you should be able to see the amount of time remaining before that lobby expires.
Okay.
I hope that answers you, Nancy.
Yeah, sure, it does.
Awesome.
So, is anyone maybe having issues accessing the lobby? I can see quite a team here from who work on CR every other day from SilentSec. So I'm sure we'll be able to help you. So in case you're having any issue, like you've heard from Lawrence, that the lobby will still be available for a couple of hours. So you can take advantage of that to maybe do more and also recap on what our guest is presenting. So also we have hosted, like I said in the when we started the session, that we've done a number of sessions besides Nairobi. So feel free to maybe revert on our YouTube page, She Hacks Kenya, and maybe have a recap on what we have done so far. So in case there are any questions, I don't know if the fact that there are no questions, if that's a good thing or a bad thing, but I hope you are all at par with our guests. So in case of any questions, feel free to ask. Maybe you can unmute, or you can maybe have it in the chats. Yeah, in case of any questions, feel free to ask. Okay. So no questions. Okay. And let me just share this on YouTube as well in case someone would want to try that.
All right. I'm on a different network right now, which is a bit more faster. Let's see.
Okay.
Yeah. Awesome. I think this might work. Let's see. Let me just refresh guacamole. Awesome. I'm good. All right. Let me share my screen now. Hope this one does not let me down. The other one did not restart very well after Safaricom. It did not restart very well after the blackout. So I think it's having errors. I need to reboot it and maybe work with it later. All right, so we are looking at the views. Let's see how this one works. Was there any questions before I left?
No, not yet.
All right, let's continue then. I think this time I'll be more faster, and you actually be able to see what I'm doing. So we are going to work with streams directly. We're not going to go to the imports. We're going to just work with what you have here. And let's see if I move it, if it's going to go in. No, it doesn't go in. All right, anyway, it's okay. And what we want to look at is going to look at how the IP tables are being called by this toolkit. So that's what we started on. Right now the internet is much more better. I can actually be able to do. So it was the internet issue. I can actually do more. So as you can see, there's a string command, which is being called by the binary, by the implant. And we're going to start from there. So double click on it and take down the string table. All right, so this is on this function. So actually, if you want to look at the function that actually being used to call this string, you can double click on this, and it takes you directly to where the table is, and you can analyze now from there. So what I'm going to do is I'm going to click Control, and I'm going to scroll up, so that because I'm using a Mac machine, and actually be able to analyze that table. As we said, as we go up, the basic thing about analysis when you're doing malware analysis is that it's like you are trying to open a small box, and you find other things inside that box, and you try to figure out which box are you going to go to, so that you can be able to see the next part of the puzzle and try to be in a position to solve it. All right, so the first thing we see down here is that when it routes that information via IP tables, so I'll make it bigger so they can all see it. it's actually a very big function. Come on. Okay, there we are. So it's actually a very big function. As you can see, it's actually calls that part of the netting. And then when it executes the file, this is actually when it's executing the IP tables command. It's actually calling it all the way to accept that, all the IP tables, the input. Then it actually opens some levels of where the file is supposed to go to. It could be a /dev, and then it sets it, and then just continue going through and see what happens next. Okay, that does not give us as much information as what you're looking for. All right, let's go to the next one. And these are actually a lot of strings. You can actually give you clues on where to look for other common operations that this thing might be actually be doing. I'm going to go to the strings again. Okay, let's start here with sockets. These are basically the normal functions it's actually calling from the Linux API. And what I'm looking for is where it actually does, it actually builds a memory level before it deletes it on memory, so that it cannot be noticed by anyone who is doing analysis on it during when it's actually operating. Okay, it's not there. It's all about searching this thing. I didn't get time today to actually analyze it, and so I can have the direct process to go for. All right. Okay, let's look at this being dev. Let's look at this one. Okay, this is the main one. Okay, let's see how it does it. This, oh yeah, now we are there. Let's start from here. I will just close I will just put the string beside. And here is where when it starts. So the first thing it does, it will actually try to make a normal dev memory level kind of call, and then it will try to make sure that it gives it a name from a list of names that it has, and then it will go ahead and call it. And then when it calls it, it will go ahead and run the file name. So here we can see that first of all, it tries to develop a name or make a name that it's going to use as a process. And the process is going to use, it can call itself a process name that is legitimate process name, legit process name. So by therefore, you can see some of these processes which are here are actually rigid process names that it will try to actually use, which is the list down here. This list up here. And after it does that, it will go ahead and now maybe it will call itself maybe system D journal, or it will call itself maybe audit D something. And then when it runs, it will make a 0 kind of byte level of a PID. So this version you're using, it will give it a name called, let's read that name, inside val, which is val run znet d dot log. So this is actually in some machines you'll find it. It will call itself maybe. It will give itself a PID name. I think this one was meant for a Solaris machine. This binary we are actually going through. Maybe that's the reason why it was giving it server.log. All right, so when it does that, what's next? Let's go through the graph and see what happens next. We are not going to go through all these processes. We are going to actually just understand the next part of what it does next after it actually calls that log. It's supposed to actually zero it into 0 bytes, and then it works from there. Okay, what is this? Does this one take us? So one of the best ways is actually can point and at one point of the location for the function to see the next part of the movement by the lock. Okay, let's analyze this down here. So it has already made that dot log. So the first thing when it does a dot log, it means it has already opened it on dev something or /dev on memory, most likely /dev.shm. I should make sure we have that somewhere down here. So we just need to have to look for it. It's not defined. Not defined. Let's look at this. I think this is where it does the timestamp thing, because this looks like a timestamp for the date. So that it can actually look at as if the file is old. All right. I'll look at that later. Let's just mark it up. Let's mark it up somewhere. Just write it down. It's on 717986919. All right. Let's continue to the next one. We're just going to use strings for now, so it's going to take us longer to actually be in a position to do all the questions and make sure the questions are answered. The other operation it does is mostly likely to make sure that it locks this toolkit and runs it, making sure it's on the right properties. So let's go look at those locks. Come on, open it up. Yeah, here we are. And okay, open up. Here we are. Awesome. So it will actually go ahead and try and delete delete the process. Come on. Yep. It will go ahead and try to do ahead after it runs it on memory, and maybe it's going to be /dev/shm. As I remember that's where it was actually pushing it on memory and it runs it, and then it will make sure that the file is already deleted on memory level, so that we can already see a 0-byte log file on process level, and all right, let's leave it up there. Let's go for the next one. Okay, let's look at this call. So one of the best things is actually to see to actually look at these calls directly. This is where it has it is calling the, we don't need that one. You had already looked at that before. Okay, let's look at the environment for the fork. It can give us more ideas. We've done it. You have done that too, or you don't need to look at that again. This is when it was calling the names that's going to use. Okay. What else do we need to look at? This is when it calls it, that we've already done. Okay. This version you're using, I think it's a little bit very old. That's the reason why I'm not getting the things I'm looking for. It seems like it's not the one you actually was supposed to study. I think you're supposed to look at the other CUPC, but it's okay. We started with the wrong one, but anyway, we are going to look at the one we actually have. As you can tell that the first thing it does, it is always going to actually do a type of a connection on the remote. So it's actually going to hook itself after it runs the routing, where it actually runs the packet filtering and nuts itself on a service port that's running. It could be a service port on port 80, and it will try to hook through via what we saw with the IP tables. So obviously here we have to specify that the IP tables on the target machine. So we need to remember that on a port that is running maybe mostly a web server, which you're going to actually be to emulate when you start studying it. And it's going to go ahead and run the connection emulation for accepting and setting up the socket and looking at the environments as it comes, as it actually loads up on the service machine, on the service of the machine. Let's look at the next API, most likely listen. Okay, not much information there. Let's look at the next API, set socket. No, we don't need that one. That one you've already seen. The other one is maybe environment, the one that was calling the, okay. These are the ones which are being, actually the exports that was looking at when it executes. We are looking at the older version. So what I'm going to do is I'm going to close this one and I'm going to go to the newer version, which was maybe CUPS3 file that we did before, because this one is not giving us all the files we need to look at. And to do that, we can always open a new instance and do okay. It happens, you go and use the wrong one. Let's use this one. Actually, you can see when the size is different. This is one that's correct. We'll be having the more information we need. So it's always a good idea to actually look at all the implants that you might be having for a certain target to actually be able to understand, because that I think it was not it was an older one, or maybe it was they had done some higher levels of packing or something. All right, this one you can tell it has only one export which they have manually added, and then you have also the start work function, which starts the main entry of the binary. So actually, if you start, you can see, this is the right one now. Yeah, we have the right one now. It has more information that you can actually look at, and we understand the binary. No wonder we had an issue before. This is the environment. Let's see what the environment has. And you can see, yes, this is the right one. It has more information, because from here, this is when it starts doing, after it understands the connection, the environment of the target, it will start loading the stuff we were actually looking at before. Actually, if you actually check them right now, you can see it actually does the socketing, and then it opens a socket and hooks on it. And then you can have it listening so that the control machine can connect to it and launch the shell, the reverse shell. Now we're on the right spot. We are looking at the wrong binary. No wonder. All right, so let's look at the strings of this to actually do a shortcut. If you don't have, if they have encrypted the strings, it could be a different story altogether. So strings. Yeah, now we are good. You can even see this the data calls the library, the library, and now it goes all the way to the virtual addressing of the target library. Okay. Strings. Now we're okay. Connect. Maybe look at the connect one for connecting. Oh yeah, that's the same one from the older one. Let's look at much more weird strings that this implant can actually be using. So I'll try to go as slow as possible this time, because I had not done much analysis today for this. I didn't have time to do it. So it's like I'm starting over again from scratch. Let's look at the routing, how the routing was done by this binary. Okay. Okay, as you can see, this one, by default, it's also doing the same thing. It's opening up the same PID after it runs. So it actually finds the name it's going to use, just like the other one. This is the newer one, which has more data in it. Then it runs the file from /var/ all that. And then, yeah, you can see this is where it does now it looks at the time, and then it does time stomping. If you actually look at this directly, it will tell you it actually does the time stomping functionality for the timer. And it changes the time to a certain date, which you can always analyze later. So obviously, if we know how to do the timing stuff, I think this should be around most likely 2018, 2019, I'm not sure. I mean to the 8 to the 9 there, then it runs the binary on a target machine. Yeah, which is okay now. All right. Any questions so far? As we look at the next one, the next part, because we wanted to look at how it runs the binary before it executes it, and then does the time stomping. And you have seen the graph that does that. Any questions so far? Any question? I'm hoping I didn't lose anyone. A moderator?
Yeah, I was trying to check the chat. I don't see any questions. So for now, yeah, you can just proceed.
We are good so far.
Yeah.
So the next thing we need to do, Kat, is how after executing, we can actually try to see how after it executes what it does next and what the controller might look like on the target system. So what I've done is that on this range, I've built a server which is actually compromised with the software. You can actually log into it. So what I'm going to do is I'm going to do the same thing. All right, so I'm going to do a login to the target machine and search. And I'm going to actually connect to it. And the file, the executable we are looking at is called door. It's actually almost the same one we had before, which is this. And I'm going to execute it. And the first thing we do is to see whether it's actually running. So to run it, what you're going to look for is packets. You're going to actually go ahead and search within the stack. And you're going to look at, you're going to see what type of packets it's actually running. So if you can look at packet, you can tell that it's actually already setting packets. So this is actually the version of the call it does, which is actually having the string for the password that the user who connects for remote should connect to. I think we should actually be in a position to see this on this toolkit when it's running. So let's just look for it. It should be packed with strings. The problem is I can't remember where it was. Okay. There's a problem with doing analysis because you have to go through every call and understand what it is actually calling, so that you don't get lost. All right, I think you're the right one now. Let's just continue scrolling up until we get to the right part where it's calling it, so that you can scroll us together. All right, so what I'm going to do is I'm going to make it a little bit bigger so that we look at it. All right, here we are. All right, so as you can tell, it tries to do something here, which is this. Let's just write it down: QMGR TFIFO I'm not sure, I can't remember what this is, but we'll come back to it. I think it's better if you write it down. Q QMGR space underscore L underscore T V4 underscore T V4. I'm not sure about this, but I'll check what it is as we go on, because obviously we get another clue as we do the analysis from here. Then we have being SH. Yeah, that's being SH is being called directly. And then here it's actually getting the home directory of actually the set directory for the variable for home. And the home of where it's supposed to connect from is calling it from TMP. Ah, now I get it. So obviously when it executes it, it will give it a name here and take it to TMP folder. And that's where the file it's going to be at. The file that's actually executing, it's going to be at. So actually, if you go to this server and go to TMP, let's see what's there. And it will try to actually open a Okay, why can't we see it? Oh, it's because maybe you're using a different. But this actually, it actually sees the path to that file. Okay, this is just the path, huh? I think PS1 TUA at. Then after that, it will try to go ahead and pick up the path, or rather the environment for history files. Then after that, it will dev null the history. So the next thing is actually dev nulling. If you people know what dev nulling is, or rather deleting on memory the history, or the operation that the operator does, the operations on target machine. So we're getting there. Then we continue. There's something it's doing in the MySQL. I'm not sure, but let's put it there. We're going to look at it, obviously. Then it does dev null. I think it's actually deleting the MySQL also path, or MySQL history, or doing something with it. And then it actually picks up the part where the kernel or where the keybarrows is, and then it's trying to execute something on keybarrows. So let's go ahead and look at it. Local bean. Local is bean. X, xi, x1, x6, bean. Okay. Just give me a minute, I'll figure out what they're trying to do here, and I'll let you know. So there's something about postfix, as you can see from there, which is actually, it's a path to where the master is. So what does that do with everything? And you have a call of 3458. You also need to understand what that does. 3458, we don't know yet, but if you look at the functions, we might find out. one, 3458. Which looks like most likely it's a socket. Let's look at it as a socket. Okay. We don't know yet, but you have to go through the binary to see what it does. So it does that. It calls the socket, and then it defines the argument for socket, which looks like there are two, or actually, no, three. Okay. Went the wrong way. Okay, up. Go up. Just give me a minute. I'll figure it out. Give me a minute. I'll find it. I'll find it. The most important thing is first of all to see how the tables are, how they're calling each other, and what's calling what. Let's hang on there. We're almost there. I think it's like it's actually calling it. It's actually trying to develop a TTY. Now, which TTY is it? Or it's actually calling a TTY on target after execution, and it actually picks it up. So where does it pick up the TTY after it executes it? On socket, because you can see that's a socket actually, which is hard coded by these guys on port 3338 on 3858 or 3458. The issue is I can't tell where it is. What you do is just you have to go ahead and search and find it. I know time is running out. It's almost it's almost 8:40, and this is the problem when you're doing analysis. It takes a lot of time and a lot of bandwidth on your hand as you try to figure out which call is which when you're doing analysis on a target machine, on a target implant. So this 58 looks like a socket, which is actually being called, and we can't tell what calling it, but you can tell it has there's like a TTY that it's forked by a sub function, which goes ahead and sets the PTY or the TTY on the target machine after it actually calls the backdoor, and after it has already done the dev nulling of those history files that we were looking at before. Anyway, because of saving time, we are going to go back to the strings, and we continue from where we left off with the strings. Analysis can take a lot of time in your life if you are actually patient. That's the most important parts when you're doing analysis on a target file. I think I've seen something here which can actually help us that we were looking at before, which we didn't know what it is. There's this pickup FIFO. Okay, let's look at it. This is one we had seen before that was giving us a little bit of issues. We didn't understand what actually it was doing before. I think it's a file which it tries to call, which is actually a default. It's actually part of the files that is actually calling to actually be in a position to hide itself as a normal process on the Linux target machine. So the question I have is, what is this? Is it the same? No, but there's something going on there. So far we can tell timestamps itself, timestamping. And then it adds the files here during the connection after the socket is developed. So the socket from the remote controller, high possibly the controller, the control server most likely. And as you can tell from here, the packet is actually initiated. It has to wait for a certain magic packet, and the problem is that we can't see it from here. Let's just see if we can find it from the strings. We are trying to save time, but we can't find it. So come on, open up. No, that's not the path. That's the thing about analysis. You go to the wrong path all the time, and you find you're losing time when you're doing analysis on the machine when you're doing analysis on a specimen. Okay, let's start from here. No, you're not the right. That's not the right place. Okay. No. So where they put the magic packet? Okay. I think you look at the API, the export. Let's look at the export first. This export environment, and it might give us the point where the magic packet is called, because you just need to see the password that they use on the magic packet, packet function. It actually most likely it is already hashed, so we just need to unhash it, or maybe it's actually opened by either. All right, I can't find it so far. Okay, it should be there when the file name is called. This is where the port is opened. It actually gives us the names. All right, I can't find it in time, and the time is running out. So what I'll do is that I'll just go to the demo of how the implant works because of time. But if you actually look at how the socket is being opened and which file is actually calling, which is supposed to pretend to be a normal Linux process, you might be able to go ahead and find the function which is calling which is actually supposed to be the main entry of this binary. And it's supposed to like pick up a path of of the files, or I mean, pick up a part of the files which can actually be called, or it could be maybe udevd, or maybe milgetty, or maybe console key, like you're seeing on these on the strings here, and then it will actually go ahead and call the magic packet before it opens the socket. So by default, the magic packet will have the password, and actually, if you look at this process here, you can see it has the 0x75, which actually opens up all this opens up the packet, which actually calls a password called just for fun. I wanted to show you that, but I can't find it yet. It will take time for me to find it because I can't remember what it was, but I remember it was part of the entry point of the binary, as the binary was called on environment. And I don't know why I'm not able to see it right now, but anyway, I wish I had time today. I could have already been in a position to do that, and so that you can actually see how you decrypt it and you're in a position to see the password. So what I'm going to do now is that I'm going to log into the other server, which is this. No. This one. This is going to be our controller. We're just going to save time because time is running out on our end, and $188. Let me search for the password. 1 minute. All right. So for those people who have actually been able to get a controller, you can actually go ahead and search for it. For those people who have access to CyberEdge repo, you can download this file from the project files where we have all the binaries kept for analysis by CyberEdges, and you can go to the repo. And those people in CyberEdges, you can actually go here if you have access to it, and then you just download the control log, which is a controller for the binary that's used to actually work with the implant. So what I'm going to do is we're going to do the same thing, and the controller, I think it is on BPFDoor, and here it is. And what you're going to do is that you're just going to make sure that we call this file because it's already running, and you're going to use the magic packet, which actually goes ahead and does just for fun as the password, and it's going to connect to this, and you'll notice that we will have full access to this target machine. And this target machine by default it is on 2354.226.117 or 17. And to call it, we are going to actually go ahead and look at how the BPFDoor toolkit looks like. So you can always do the control how it looks like. You can always do strings, controller, or control lock, and go ahead and do more to actually look at the options that it has. And it does normal exports for the files and stuff, and it calls the normal APIs we're seeing on the other side, and then it just sends a magic packet directly to the target system, and then it connects to it. So what you're going to do is that we're going to look at the options it uses for that. So by default, we should see them, which is option 1, which is H, which is most likely hosts. Then the destination, the target machine of the port you are going to actually be using. You're going to actually filter our packets from when it executes on this target machine, because already executed. Actually, by therefore, if you actually look at the start, you can see it is still running. And if you look at maybe you do ps out grad dot, you see it is not there because it's already gone. And though the file name is there, which later the attackers usually go ahead and delete. But if you look at the proc, it's actually hiding itself somewhere there using a certain, using maybe a dev.shm. Then you have S. S is the port that you want to use as your listening port. And so for us, we're going to do the same thing as the way the attackers did. So we are going to execute control lock, and we're going to specify the host name we're going to go for, which is this target. So the IP address is 232.54.226.117. And go ahead and just paste it there. The next thing you're going to do is to make sure that we specify the port. We have to make sure that our port is open. Is it running Apache? And Apache is running on port 80. You can tell from here. You can always check by doing a CTL status to actually notice it's actually running. So the best one these days is Surface Apache 2 status to actually tell you it's actually running. So we are going to actually hook into that port, and we are going to specify port 80. And then you're going to open up our own port by using the S for the service that you're going to actually use for listening. And let's make a port like maybe for 45456, maybe for that reason. And then you're going now to send the magic packet. And this magic packet is why we're actually not seeing it from here. It will need for us to do a little bit of more analysis to actually find it. And I think it should be something to do with this 358 service. And if you go through here and analyze this whole thing, there's high possibility we might need to put it on a debugger, but there is no time for us right now, because if we actually put on a debugger, we might actually be able to see it on memory level. And time is against us. You can see it's almost 9. So I didn't want us to go through that level of debugging and because of time. But one day we'll do it. So if you analyze it, you get the password. By default, the magic packet, you have the password, which is just for fun. And then it will challenge this target machine, and it will have access to it. And by therefore, right now, if we do W, you'll notice the user who is logged in from machine here is me, actually. So obviously, that's the target machine. If you do uname -A, you come here and do the uname -A, you see it's actually the real IP, the real machine. IPA will tell us we are on the target machine directly. So this is how they were covertly being in a position to log into the machines after doing after implementing a housekeeping implant. That is a BPFDoor. All right. Any questions so far? I don't know if there's any question you have not answered. If there's any question you have not answered, please let me know right now. That was on the CyberAegis QA, so that we can go ahead and answer it from here, because all the answers are here on these 2 implants that you've been given. Any question? Moderator, there's more time? Yeah, go ahead.
Okay. Sorry. Yeah, so I think if we have quite a chunk left, maybe we can do a part 2 next week, because I feel like time is far gone. Maybe we can just stop at that. So maybe you'll direct me, or we can have a side chat after this. If that works.
Awesome. So obviously, if you had time, we could have gone through it step by step in a way that we look at the export environment and we walk through it from there, because this is what I was trying to avoid, starting from here step by step all the way from that function, because that will take longer to analyze it, and we didn't have a lot of time to do much of that. The other thing is, the other good idea is to actually go through this function on this side. They also help a lot to actually understand how each function is called. So when you have time, we can have like a longer analysis to actually be in a position to see it through the whole way. But the good thing is that the source code for this implant was leaked. So if you want to look at it, it's on Pastebin. I think also on CyberEdges, for those people who have access to this, if you go to this part, you can actually be able to actually pick up the source code. It's also there, and you can look at it. So it's a good idea to actually see it if you want to. Yeah, so if there is no questions, I think then I'm okay.
Okay, thank you so much for making time to take us through this session today. Yeah, I believe the others who have joined us maybe before, maybe a bit late, or others maybe have dropped off from the call a bit early as well. So this session will be live on our YouTube channel, like I said earlier on, at SheHacks Kenya. Feel free to revert anytime. We'll have a discussion with the guest on when we can have part 2 for this as well, because I believe it's been very insightful. Myself, I think I've learned so much as well. So at this point, I'll just, maybe you can just come to a close. But thank you so much for making time and for joining us. So for the next one, we'll definitely communicate on our social at SheHacks KE. So thank you so much, everyone, and have a good night.
Thanks so much.
Good night.
Thank you and good night.
All right, good night.
Thank you, Gishuki. Good night.